Welcome to section 4.6. Variation of parameters is another way to find yp, a particular solution of a second order non-homogeneous linear differential equation. The first way would be undetermined coefficients. So one of the things you'll have to do in variation of parameters is integrate quite a bit. And so here's some common integrals that might come up from our integral Bible in case you've forgotten them. Here they are. And then here's some common integrals that require parts. These are basic u sub, and then cosine squared and sine squared both need half angle in order to integrate. So let's recap what kind of differential equation we can use UC on, undetermined coefficients. Remember, the rules are constant coefficients, linear, and the driving function f has to be a polynomial, sine, cosine, exponential, or a product of those functions. So the first one looks good. It's linear, constant coefficients, and over here we've got an exponential and a polynomial. Second one, no, this one's no good because it's not linear. You're not allowed to have y prime squared. So that's no. Third one is no because the coefficients aren't constant. Down on the next row, again, we have a no, LNT is not allowed. Next one, this is a yes because 1 over cosecant is not allowed, but 1 over cosecant is sine t, and that is allowed. So that one's fine. And then the last one looks good too. All right, variation of parameters. This can be used for higher order, but it would require computing 3 by 3 determinants. Not a lot of fun, so we're going to stick to 2 by 2, a second order differential equation. And the difference between this and UC is that you do not need to have constant coefficients. So I've broken this down, the solution process, into 4 steps. Step 1, make sure you have a monic differential equation, meaning the coefficient of y double prime has to be 1. Even if it's a constant, you need to do that. And that's step 1 because that's going to determine what f of t is. So f of t will depend on the fact that this coefficient is 1. Then you're going to find a fundamental set for the associated homogeneous differential equation. So a y1 and a y2, you're going to label them. It's important to label them, and it doesn't matter how you label them, just stick to your labels for the whole solution process. You're going to find their Wronskian, and so at this point you'll have a list of 4 things, y1, y2, f, and w. Then you're going to find 2 new functions called v1 and v2, and your book doesn't really make it clear how to find them, but here are nice closed formulas for how to find v1 and v2. v1 is the integral of negative y2f over w, and v2 is the integral of y1f over w. Finally, what you do with those 2 functions is you can form your yp by letting it equal v1 y1 plus v2 y2. Now, the reason this method is called variation of parameters is that instead of a solution being c1 y1 plus c2 y2, where the c's are constant, we're allowing our parameters v1 and v2 to vary. These will be functions of t. All right, so let's just jump in and do some examples. First one, we're going to use VP, that's variation of parameters, to find both YP, a particular solution, and the general solution to this differential equation. Now, we could use UC on this. This is a totally allowable DE for UC, so you might want to do it both ways and see if you get the same answer. Step 1, make sure you have a monic differential equation. That's done. The coefficient of y double prime is already 1. And so at that point, I can identify f of t. It's this function over here, so that's e to the 3t. Now we need to solve the associated homogeneous to get our y1 and y2. So our roots are r equal, I already factored the characteristic equation for us, negative 1 and 2. And so yc is c1 e to the negative t plus c2 e to the t. 2t. Now, y1 can be either one of these, e to the negative t or e to the 2t. I'm going to let it be e to the negative t. y2 is going to be the other one, which for me is going to be e to the 2t. So it doesn't matter how you label these, but once you make your label, you have to stick with that for the whole solution. The Wronskian is going to be, it's been a while since we've done a Wronskian, but we put y1 and y2 across the top row, their derivatives across the bottom row, and then we take the determinant. So straight bar is the notation, and that's 2e to the t, adding the exponents, minus a negative is plus e to the t, so that gives us 3e to the t. Now, if you had switched your labels, if you'd made y1 e to the 2t and y2 e to the negative t, then your Wronskian would be negative 3e to the t. You'd still end up with the exact same yp at the end, but each step would be slightly different. All right, step 3. I'm going to compute v1 and v2. v1 from the first page is the integral of negative y2f over w. This comes from Cramer's rule, by the way, dt. I have a proof of this at the end, which is the integral. Okay, my y2 is e to the 2t, so I have negative e to the 2t. My f is e to the 3t, and my w is 3e to the t. So that's the integral of negative 1/3. And how many e's do I have? I've got e to the 5t on top, e to the t on the bottom, so that's e to the 4t dt. So when I integrate, I get negative 1/12 e to the 4t. Take the constant of integration to be 0. All right, so put that on hold for now. v2, we'll use that in a minute. v2 is the integral of y1f over w dt. I suggest you write these formulas down each time you use them, and it just helps you to remember them, actually. This is the integral of e to the negative t, e to the 3t over 3e to the t dt. So that's e to the 2t on top over e to the t gives me e to the t. So that's the integral of 1/3 e to the t dt, which is just 1/3 e to the t. Okay, now we put those together with our y1 and y2 to form our yp. So step 4, yp, a particular solution, is v1 y1 plus v2 y2. So make sure you know what to do with these v1 and v2 once you're done with them. Some students get caught up in the finding of them, and then they forget what to do with them. So this is what you do with them. So v1 y1, this is negative 1/12 e to the 4t, and my y1 is e to the negative t, plus v2 y2, 1/3 e to the t and e to the 2t. Okay, so each of these is going to simplify to e to the 3t. So I'll have minus 1/12 e to the 3t plus 1/3 e to the 3t. And when I simplify that, I get positive 1/4 e to the 3t. That's my yp. That's a particular solution. Now, in this case, I want both the particular solution and the general solution. So my general solution, remember, that's just yp plus yc. So y equals, or copy down yp, 1/4 e to the 3t, and then I add on yc, which is up top, c1 e to the negative t plus c2 e to the 2t. Was it 2? Yeah, it was. Okay. So there it is, 4 steps. Let's do another one. I've picked ones where the integration might bother you a bit. So this one, step 1 is already done. Coefficient of y double prime is 1, so we can go ahead and copy down what f of t is. It's cosecant squared of 2t. My y1 and y2 will depend on my solution to solving the associated homogeneous differential equation. The characteristic equation is r squared plus 4, so I have complex roots, 0 plus or minus 2i. So I went ahead and wrote down my yc, and I'm going to let y1 be the cosine 2t, and I'll let y2 be sine of 2t. I could switch it, but then my Wronskian will be the negative of what I'm going to get here. The way I do it here, I'm going to get the Wronskian is 2 cosine squared 2t minus a negative, which is plus 2 sine squared 2t. Factor a 2 out, cosine squared plus sine squared is 1, so my Wronskian is 2. Okay, and now I'm good to go. I've got all the ingredients I need for my v1 and my v2. My v1, remember, is the integral of negative y2f over w, which is the integral of negative y2 is sine 2t, f is cosecant squared 2t, and I'm dividing by 2 dt. Now, cosecant is 1 over sine, so this just simplifies to the integral of negative 1/2 cosecant of 2t. This is just basic Bible formula. The integral is negative natural log, so a negative negative gives me a positive, and I bring out a half, so 1/4 ln absolute cosecant 2t plus cotangent 2t. If you haven't used this formula in a while, you may have forgotten, and that's okay. And take the constant of integration to be 0. v2 is the integral of y1f over w. So that's the integral of cos 2t. F is cosecant squared 2t over 2 dt, which is the integral of, let's see, 1/2. And I can write this as cotangent times cosecant. Cotangent 2t times cosecant 2t. Well, the derivative of cosecant is negative cosecant cotangent, so I'm going to get negative, and 1/2 comes out to give me negative 1/4 cosecant of 2t. Okay, we're almost there. We only want a particular solution in this case. We don't need the general solution. So yp is v1 y1 plus v2 y2. All right, so this is going to be a little bit long. 1/4 ln absolute cosecant 2t plus cotangent 2t times y1, which is cos 2t, plus v2, which is negative, so I'll just put minus 1/4 cosecant 2t times, that's v2, now I want y2, sine 2t. All right, but cosecant is 1 over sine, so these guys just kill each other off, and I end up with minus 1/4. So my yp is 1/4 ln absolute cosecant 2t plus cotangent 2t times cos 2t minus 1/4. Wow, that's a mouthful. All right. The last one I'm going to do with you is an example of non-constant coefficients. So this one has coefficients that are variable. So we could not use UC on this one. Now, because of the fact that these are variable coefficients, it's kind of hard to find a y1 and a y2. So that's been given to us. We're already given the fundamental set, so we don't have to find y1 and y2. And I've already written those down in my box because those are given. Now, be careful, my f of t is not t squared, because in order to use variation of parameters, you have to have the coefficient of y double prime has to be 1. So step 1 is not done. We need to divide by t. So y double prime minus t plus 1 over t y prime plus 1 over t y equals t. So my f of t is actually t, not t squared. We don't need these coefficients here. Yes, they're interesting, but we're not going to use them in our solution. All right, and the last thing we need in terms of ingredients is w. So I've started us out. I put y1 and y2, and then the derivatives on the second row. Now I'm going to take the determinant, e to the t minus t plus 1 times e to the t, which is going to give me negative t e to the t. All right, and I'm good to go. Step 3. V1 is the integral of negative y2f over w dt, which is the integral of negative y2 is t plus 1, f is t, and then w is negative t e to the t. This is dt. So this is going to be the minus kill each other off. These t's kill each other off. So I end up with positive t plus 1. And then instead of writing it over e to the t, I'm going to write it as times e to the negative t, because this is going to be integration by parts. It's much easier if I write it like that. So for parts, I'm going to let u equal t plus 1, du is dt, dv will be the exponential term, e to the negative t dt, and v, I integrate to get negative e to the negative t. So remember the formula, it's uv minus the integral of v du. I want uv minus the integral of v du. So uv is negative, I'm going to factor the minus out, negative t plus 1, e to the negative t, and then what do I have? Minus the integral of v du. V is negative, so I'll make this a positive, e to the negative t dt. Almost there. Negative t plus 1 e to the negative t minus e to the negative t. Take the constant of integration to be 0. V2, don't worry, this is a little easier. V2 is going to be the integral of y1 f over w dt, which is the integral of e to the t times t over negative t e to the t dt, which is the integral of negative 1, which is negative t. And finally, I think this is step 4, yp is v1 y1 plus v2 y2, which is negative t plus 1 e to the negative t minus e to the negative t all times y1, which is e to the positive t, plus v2, which is negative t, so switch that plus to a minus, times y2, and y2 is t plus 1. Okay, so this is going to simplify quite a bit. When I distribute this e to the t to this guy And to this guy, I get 1 because you add the exponents, I get e to the 0 and then e to the 0. So if I simplify, I get negative, I'm going to distribute the minus, negative t minus 1. And then here I'm going to get minus 1. And then minus over here, t squared minus t. So make sure you follow that, pause it if you need to, and just make sure that you understood where all that stuff is coming from. And then if we do our final cleanup, we get minus t squared, we got minus 2t, and then minus 2. And there's our yp. All right. And lastly, I just want to summarize the two methods for you. By the way, you have two homework problems to do. This one, fairly straightforward. This one's super easy. The integrations are very easy. Okay, undetermined coefficients versus variation of parameters. So the kind of math. Undetermined coefficients in general uses algebra. That last step, after you found your trial yp and put in yp double prime and yp prime, you end up solving a system of equations, like maybe 2a plus c is 1, bc equals 2a plus c is 0. You'll end up with a system of equations, and you'll solve them for the coefficients. So that's algebra. The kind of math you're going to use for variation of parameters is calculus, because that V1 and V2 are very heavy on the integration. I mean, they're defined in terms of integrals. So calculus versus algebra. Restrictions on P and Q. You got big restrictions for UC. They have to be constant. For variation of parameters, very not stringent condition, just continuous. That's all you're asking. All right, restrictions on F. Yes, for undetermined coefficients, the restrictions are polynomial, sine, cosine, exponentials, and products of those and sums of those terms. No restrictions for variation of parameters. F just has to be continuous. So you've got two methods that you can use. Some students like one more than the other. It really just depends. And some problems, like, for example, this last one we did, can only be used using variation of parameters, but many can be used using both. Anything you can use UC on, you could also use variation of parameters on. So this one you had to use VP on. We could not use UC on this. So we had to use VP on this one and on the last one. And this first one, we could have used either method. All right, and that is the end of this section.